Hello, everyone. I'm Han-Seok Son, and I'll be your instructor for IE 533 Linear Programming course. And this course introduces the theoretical principles of the linear optimization, and also its application to solve the real-world problems. Since I know some of you are very new to the Canvas system, our course management system. So let me show you how to navigate our class Canvas system, okay, website. So first of all, let me share my screen. Okay. So if you type in learn.nmsu.edu in any web browser, then you will get this screen, right? So first of all, I highly recommend you to go visit either student support up there or down here, the student Canvas FAQ sessions, okay? So it's gonna be the identical information, I believe. So from there, you will learn very useful information, such as the navigating the Canvas system, or notification preferences, and how to check your grades, and so on. Okay, so when you have time, please go visit the here student Canvas frequently asked questions. Okay, now if you log in using your NMSU ID and password and choose courses from the sidebar menu, and then IE 533 linear programming, then you will get this screen, right? So if I go further, let me choose student view. So it's going to be very similar to what you're going to see from your end. Okay, and also let me disable my video just in case, because previously I had some issues related to internet bandwidth. So let me disable my camera for a while. Okay, see here. Okay, so here, first of all, you're gonna notice that there is a couple of the notifications here, right? So when you see this symbol, microphone symbol, that means you do have new announcements, okay? So you can check those announcements from here or just clicking one by one down here, okay? And also you're gonna see that there's a couple of the class activities coming in the deadline, okay? So you're gonna see that homework number 1 has been already posted, and our project proposal guideline, also our term project guidelines available from the assignment tab down here, okay? And also you can check your grade by clicking grades, and you can download our lecture note from here. So whenever you see this symbol, that means you should be able to download the corresponding files, okay? And later on, you're gonna see the similar symbol right beside lecture video. So you can download our lecture videos from here. And in this column, suggested reading column, you can see additional reading materials for example, Lindo manual and Lingo manuals. Okay, and also these are the recommended reading materials from our textbook, chapter 2 and chapter 2.2. And also in the last column, you're going to see that some other class activities, including our homework solutions. You can check the homework solutions down here. And I will try to keep you posted the coming deadlines. So one for the project proposal down here, and project written report and presentation slides and recordings also due on Sunday, the April the 30th. Okay. Okay, so first of all, let's look at our core syllabus. Okay, so this is our course description. So linear programming, problem formulation, and simplex method, theory of linear programming, dual problems, transportation, and post-optimality analysis. Okay, so of course, this course is a problem-solving oriented course based on critical thinking. And our discussion will be mainly focused on the linear programming formulation, modeling, and its solution approaches, okay? And the topics includes the linear programming modeling. So in this section, we will explore how to construct LP model for solving the optimization problems. And also some of the optimization solver packages like Lindo Lingo will be introduced. And the revised simplex method will be also covered, which is very well known as the simplified version of the original simplex algorithm for solving any linear programming problems. And duality theories and sensitivity analysis, those are, I would say, two of the most important topics in the area of LPs, especially sensitivity analysis is concerned with how changes in an LP's parameters affect the optimal solution. So for this purpose, we will use Lindo output to handle this issue. Okay. And also we are going to talk about transportation and assignment problem as the two special topics, special types of the LP problems. And also we are going to talk about a little bit about the project scheduling, especially CPM. Okay. And critical path method. And if time allows, then we are going to talk about the integer programming and possibly the dynamic programming as well. Okay. And here's my contact information. My office is located in the second floor of the engineering complex number 3 here at NMSU main campus. And my office phone number is 575-646-2957, or same area code 575 and 646 and 4923. And here's my email address. And our my office hours are currently fixed as Tuesday, Thursdays, 9:30 to 10:30 in the morning. Or you can make an appointment with me. Please reach out to me through either email or a phone call to set up an appointment. So if necessary, I can set up a Zoom meeting with you guys. And this book is a good reading material, but it's not required, but recommended. So I just say for the best result, I highly recommend you to read the assigned materials prior to each class. So as you can see, as you can imagine, if you do not, even if you do not completely understand the readings, still it's going to help you to understand my lectures. Okay. And also some of the lecture notes will be available from the class Canvas website. Okay. And these are the references that I'm going to use. And also you can download the Lindolingo user's manual. And also you can download these optimization solver packages from their vendor website. Okay. So those are the free version. And here's the evaluation scheme. So your final grade will be based on this. So it does have academic integrity quiz and adding profile pictures and short bio, which are 2.5% each, and homework 40%, project 45%. I'm sorry, it's 55%. Okay. And I'm going to use a fractional grading scale. So the fractional grading scale provides for plus and minus grades, just like that. Okay, so let's go back to our homepage. So now I'm going to talk about our first lecture materials. So you can click on this, then you should be able to view the lecture slides in PDF format, just like that. Or if you click on this symbol, then you should be able to download it, okay? And then later on, you can open it up. Okay, so let me open my PowerPoint slides. Okay, so today I'm going to talk about the linear programming model basics. That does include a few assumptions of the linear programming. And then also I will show you how the practical solutions can be formulated as the linear programming model. And I'm gonna use a couple of examples. And just to let you know, any linear programming model with only 2 decision variables can be solved graphically. And you will also learn it probably next time. And so, oh, okay. So who is this? He's the, I'd say, the biggest guy, at least in the linear programming area. His name is Dr. George Dantzig. He's also called the father of linear programming. And he's the inventor of the simplex method for solving linear programs. And we are going to talk about the revised simplex method in this class sometime later, okay? that is the streamlined version of the original simplex method for solving any linear programming model. Okay, so the linear programming uses a mathematical model to describe the problem of concern. And here, the linear means that all of the mathematical functions in the models are required to be linear functions. And the programming does not refer here to computer programming. Rather, it means the planning. Okay, so the linear programming involves the planning of activities to obtain optimal, the best results. And often the linear programming problems, their models are referred to linear programs. Okay. Then my question is, why do we use linear programming model? So long story too short, because many real-world problems can be modeled as linear programs. Also, many other problems can be approximated as linear programs, okay? Also, the linear program solution techniques is historically very, very important. It helps in understanding the modern optimization method. It's like a stepping stone, okay? Because it can provide the foundation for solution methods for many other structures of the mathematical programs. And more importantly, the linear programming is probably becoming more useful than 50 to 60 years ago. You know, nowadays, the computer power, the computer software for solving the linear program problems has dramatically improved, right? And as a result, more and more realistically sized real-world problems can be solved. And just to let you know, last year, 2 of my PhD students got hired by American Airlines. The airline industry, especially in the United States, heavily uses mathematical optimizations for solving the airline scheduling and also crew scheduling problems, okay? And 2 other my PhD students are currently working for UPS and FedEx. So traveling salesman problems and vehicle routing problems, 2 very well-known combinatorial optimization problems that these companies, UPS and FedEx, they are dealing with on a daily basis. Okay, so before formally defining a linear programming problems, we define the concepts of the linear functions and linear inequality, okay? So the linear functions has the general form of this. So linear functions are very simple, right? And here's some examples of nonlinear functions. As you can see here, these nonlinear functions are much more complex than these linear functions, right? And a linear function, fx, is a linear function for a set of constant if this relationship is satisfied, okay? So for example, f of x1, x2 equals 2x1 plus x2 is a linear function of x1 and x2. However, down here, fx1, x2 equals 2x1 squared plus x2 is not a linear function of x1 and x2 because of this square term, right? And for any linear function, fx, and any number b, the inequalities are for example, 2x1 plus x2 is greater than equals 3, and 2x1 plus x2 is less than equals 3. Are the linear inequalities, right? Sorry. Let me drink some water. It's really dry. Yeah. Okay, but the function down here is not a linear inequality. Okay, so it's very interesting to talk about optimization problem. So simply, I decide the optimization problem is a computational problem, and its objective is to find the best of all the possible solutions. Okay, and LP, linear programming model, is a special type of optimization problem where both objective function and constraints are all linear functions, okay? And formally, the linear programming model or linear program can be defined like this. So the linear programming problem is an optimization problem for which we do these followings, okay? So first, we attempt to maximize or minimize a linear function of the decision variable. And the function that is to be maximized or minimized is called the objective function. And the value of the decision variables must satisfy a set of constraints, okay? And each constraint must be a linear equation or a linear inequalities. That is, any linear constraints has this general form, okay? So these are the just example of this. And there is a sign restriction, either non-negativity restriction or non-positivity, or even unrestricted in sign may be associated with each decision variable, okay? Now let's talk about the assumptions of the linear program. So when you write a problem as a linear program, we are making a few assumptions about the underlying process. So they are proportionality, additivity, certainty, and divisibilities, okay? So first, the proportionality. What is the proportionality? The proportionality assumption of any linear program is that the contribution of each decision variables to the objective function or the constraint functions is proportional to the value of that variables. So for example, doubling a decision variables will double the contribution to the cost functions, right? Another assumption is the additivity assumption, okay? Which is about the contribution of any variables to the objective functions or the constraint functions is independent of the values of the other decision variables. And certainty assumptions of the linear programming is that each parameter values, including the cost coefficients and right-hand side values of each constraint sets, etc. Those values are known with certainty. That means we assume that all of the parameter values are not random. Okay. Of course, this assumption is almost never satisfied in reality, right? So the sensitivity analysis that we are going to talk about, maybe about 2 months from now on, those sensitivity analysis can help to find out the robustness of our optimal solutions to the uncertainty of data. Okay, so this certainty assumption is a big assumptions of the linear programming modeling. Okay, and the divisibility assumptions. Some people call the continuity assumptions, but those are the same terminologies. Okay, so these divisibility assumptions is that each decision variable are allowed to assume the fractional values, that is the real values, right? So each decision variables are not restricted to a discrete set of values, which is integers. Okay? Of course, for certain cases, we need to use the integer variables. Then these cases will be categorized to the integer programming modeling compared to the linear programming models. Okay. Okay, so let's take a simple example, window glass company example. I've got this example from another textbook, Introduction to Operations Research by Hillier and Lieberman textbook. So in this example, certain company, Window Glass, they make doors and windows product in 3 different plants. Okay, so a batch of doors requires 1 hour at plant number 1 plus 3 hours at plant number 3. And the batch of windows requires 2 hours at plant 2 plus 2 hours at plant number 3. And plant number 1 is available for 4 hours per week, while plant number 2 for 12 hours per week, and plant number 3 for 18 hours per week available. And the profit per door batch is $3,000, and the profit per Windows batch is $5,000. The question is, what should Window Glass what should Window Glass manufacture to maximize their own profits? Okay, so this table summarizes all of this given data. Okay, so so of course in this case, to formulate the mathematical linear programming model, we begin by defining the relevant decision variables. Okay, so that's the very first step that you are going to do. So the decision variables can be defined as the number of variables and their whose values are to be determined. Okay, so this is what you want to know, or what you must determine within the model. Okay, so I gotta tell you that in any linear programming models, these decision variables should completely describe the decisions to be made. Okay, So clearly, decision maker in this company, window glass company, must decide how many doors or how many windows should be manufactured, should be produced each week, right? So that's why we define two decision variables, X1 and X2, represents the number of batches of product number one, which is doors produced per week, and X2, that is the number of batches of windows produced per week, okay? So once we define the decision variable, the very next step is to determine our objective function using the decision variable that we just defined, okay? So for this problem, what is our goal? What is our objective? We want to maximize the total profit, right? So if we let this capital Z is the total profit per week from producing these two products, doors and windows, right? Then our objective function would be, looks like this, right? So that's going to be 3,000 times X1 plus 5,000 times X2. Because from this table value, we know that the profit per door batch is 3,000 and the profit per Windows batch is 5,000. That's why you need to multiply 3,000 and 5,000 to X1 and X2 respectively. And we want to maximize total value of this, right? So that's going to be our objective function. Now we need to determine if the values of each decision variables, X1, X2, are limited by any restrictions. So according to the problem description, each batch of doors produced per week uses 1 hour of production time per week in plant number one, right? But only 4 hours per week are available in plant number one. So this restriction is expressed mathematically by the inequality. X1 is less than equals 4. Okay? So we have X1 is less than equals 4 as our first constraint, according to the first row of this table. Okay? Likewise, for plant number 2, plant number 2 also imposes another restriction. 2x2 is less than equals 12, right? And for plant number 3, likewise, 3x1 plus 2x2 must be less than equal to the available hour for that plant, which is 18. So that's why we have these 3 constraints, okay, one by one. And finally, because the production rates cannot be negative, it is also necessary to restrict the decision variables to be non-negative. That's why we put X1 and X2, both variables, X1, X2 must be non-negative, okay? So combining all together, objective function, 3 constraint sets with sign restriction. These are the this is the complete LP model for our Winterglass example problems. Okay, it's very easy, right? Okay, so now let's take another simple example. Okay, so I name it chair and table production problem. So in this example, we'd like to make tables and chairs using these Lego blocks, okay? To maximize the total profit. Okay. And here in this problem, the profits are expected $16 for each table and $10 for each chair, okay? And as you can see here, each table uses 2 large bricks and 2 small bricks, okay? And each chair uses only 1 large brick and 2 small bricks, okay? But you are limited by the availability of the materials, which means that you have only 6 large bricks and 8 small bricks, okay? So within these constraints, to maximize the total profit, how many tables and chairs should you make? That's our question regarding this example. So how do you answer? So as always, we begin by determining the decisions that must be made by the decision maker. So that's going to be the number of tables produced and the number of chairs produced, right? So we define 2 decision variables. Let's say T stands for the number of tables produced. And C stands for the number of chairs produced, okay? So we define these 2 decision variables. And of course, we'd like to make tables and chairs to maximize profit. And here, the profits are expected $16 per each table and $10 for each chairs, right? And our objective function must be maximize $16 times T, number of tables produced, plus $10, right? Times C, number of chairs produced, right? Now we need to determine if the values of each decision variables, T and C, are limited by any restrictions. We know that each table uses 2 large bricks, right? So for large bricks, and small bricks, because we are going to have 2 different constraints for each size of bricks, okay? So I'm gonna put the ST stands for subject to. So here, each table use how many large bricks? Use 2 large bricks, right? And 2 small bricks, right? And each chair uses 1 large chair, 1 large bricks, and 2 small bricks, right? So if you combine this together, what is this? That's going to be number of large bricks used for producing tables and chairs, right? And how many large bricks available? You have only 6 large bricks, right? So this number should be less than equal to number 6, right? Because this right-hand side of the first constraint shows the number of available large bricks, right? And the left-hand side is the number of large bricks used for producing tables and chairs. So the right-hand side must be greater than equal to the left-hand side, right? So similarly, if you combine these two, this represents the number of small bricks used for producing each tables and chairs, right? And also you are limited by the availability of materials, right? And you only have 8 small bricks. So it's gonna be less than equal to 8, right? And also you cannot produce negative amount of tables and chairs. So you have to put non-negativity restrictions. So combining together objective function subject to these 2 constraints and also including sign restriction. This is going to be the complete LP model for this example number 2. Okay. Okay, so we've just talked about window glass example and chair table production example, right? And both of these problems are categorized into the product mix problem. Generally, in product mix problem, there are n different products, okay, that could be produced. And each of these products consumes certain quantity of m different resources. And every unit of the product I uses a sub ij units of resources j. And given the profits of each unit item and the maximum amount of resources, our goal is to maximize the total profit, okay? I gotta tell you, in reality, many businesses, in the many businesses, the resource allocation problems take this kind of format, okay? So in the product mix problems, the decision variables represents the amount of items produced, and the objective function and constraint sets have this format, okay? So the constraints in the products mix problems basically represents the resource availability constraints. Also, we do need non-negativity restrictions, right? And the standard format of the LP with the maximization problem would look like this, okay? And just to let you know, we can use some notation to write the linear programs compactly. So in this case, our current objective function can be simplified as maximize using the summation symbol. I goes from 1 to n in this case, right? And C sub I times X sub I, right? And likewise here, the first constraint would be sum over A sub 1j xj, right? It's less than equal to 1. And the second one would be sum over A sub 2j x sub j less than equal to B2. Sorry, this is going to be B1, right? And the mth constraints, A sub mj x sub j less than equal to B sub j, right? Of course, this can be further simplified as sum over A sub ij x sub j is less than equal to bj for I goes from 1 to m, right? In a way, this expression can represent all of these constraints, okay? Of course, here, j is going to be 1, 2, n, right? It's the same. J is going to be 1, 2, n. And here, sign restriction can be simplified as x of I is greater than or equal to 0 for all i's going from 1 to n in this case, right? Okay, now let's take another example. Apex Television Company example. So why don't you guys pause the video recording and then try to formulate the linear programming model by yourself, and then come back like 10 to 15 minutes Okay. Okay, so now I am assuming that everybody have your own solutions to this example, to this exercise problems. Okay, so how did you guys define the decision variable? In this case, the decisions need to be made. Would be the number of 27 inches TVs and 20-inch TV sets, right? To be produced per each month. So that's going to be our decision variables. Okay. Okay, so where do I write down? Okay, so let me write down here. So our first decision variable would be x1. That is the number of 27-inch TV sets to be produced each month, okay? Likewise, let's use x2, stands for the number of 20-inch TV sets produced each month, okay? And our objective function is going to be maximize total profit, which would be $120 times times x1 plus $80 times x2, right? And we do have resource constraints, right? So the first constraint would be x1 is going to be less than equal to 40. So I just say this constraint shows the number of 27-inch TV sets sold per each month. That's going to be at most 40. That's why x1 has to be less than equal to 40. Okay. Likewise, our second constraint set is going to be x2 is less than equal to 10, right? Yeah. That's for the 20-inch set TVs sold each month, okay? What else? We need to handle this constraint. So I do say this is about the work hour availability. So that's going to be 20 times x1, right? So 20 x1 plus 10 x2, right? So that's going to be 10 x2 must be less than equal to 500. That's the maximum number of work hours available. So it's going to be less than equal to 500. So I say this is about the work hour availability constraint. Okay. And what do we miss? We need to add non-negativity restriction. So both decision variables, x1 and x2, must be non-negative. Okay, so combining all together, again, objective function subject to these three constraints and sign restrictions. This is going to be the complete LP model for this Apex television company example. Okay. Okay, so now let's consider another example called diet problem. Okay, again, let me give you like 10 minutes. Why don't you try to formulate linear programming model for this problem and then come back, okay? Okay, so how did you define the decision variable? How many decision variables do we need? Again, we just need 2 decision variables. Right? So let me define okay. Let me define let's say A stands for the quantity. Those are the pound, right? Quantity of feed type A. And let's say B stands for the quantity of feed type B, okay? So using these 2 decision variables, let's formulate the linear programming model, okay? Okay, so in this case, what would be the objective function? You want to minimize the total daily cost of the feed per pig, right? So this time, our objective function should be down here, minimize you're going to use this cost value, right? So 0.4 for feed type A, and 0.8 for feed type B, right? That's going to be 0.4 times A plus 0.8 times B, right? And what constraints do we have? So let's consider the first row of this table values. Okay, so using these calorie values, 800, 1000, we are going to have 800A plus 1000B, right? And this has to be greater than or equal to 8000 from here. So that's going to be the, how to say, the calorie requirement. Okay. Likewise, we can have one for the vitamin requirement, right? So using the value 140 and 70. 140 times A plus 70 times B is greater than or equal to 700 units of vitamins. So I just say this is going to be vitamin requirement. Okay. And here we need to consider one more constraint. Like it says, a further constraint is that no more than 1/3 of the diet can consist of feed type A, because it contains an ingredient which is toxic if consumed in too large quantities. Okay. So how do you express this constraint mathematically? Because it does say no more than 1/3 of the diet. So how do you express the diet? That is the total amount that you consumed, right? So that's going to be A plus B. That's going to be your diet. Because it does say no more than 1/3 of the diet. So it's going to be 1/3 of the diet can consist of feed type A, right? So it's going to be A should be less than equals 1/3 of the diet. Okay, so that's going to be the third constraint. Of course, the third constraint can be simplified by multiplying 3 on both sides. So it's going to be 3A less than or equal to A plus B. If you move A to the left-hand side, it's going to be 2A is less than or equal to B. So that's going to be our third constraint. Of course, you're going to add non-negativity restrictions for both decision variables, A and B, right? Because in this case, A stands for the quantity of the feed type A used per day, right? Likewise, B is the quantity in pounds of feed type B used per day. So again, combining all together objective function constraint sets, including the sign restrictions, that's going to be the complete linear programming model for our second exercise problem. Okay, so before we end today's lecture, let me just talk about some basic concepts associated with the linear programming problems. Okay, so the first concept is about the convex set. So a set of points S as a convex set if the line segments joining any pair of points in S is wholly contained in S. So let's assume that the S represents these shaded area in these figures. Okay, so those are the shaded areas like this. Obviously, these two are convex, right? How about this? This is not convex. Why? So in this figure, point A and B are in the shaded area, right? In S. However, there are points on the line segments A and B that are not contained in S. So I'm talking about these areas, right? So these are not contained in S. So this is not convex, okay? Likewise, this is not convex because in here, again, point A and B are in S, the shaded area, but there are points on this line segment, AB, that are not contained in S. So I'm talking about these points, right? So this is not convex, okay? Now let's talk about the concept of extreme point. So for any convex set S, a point P in S is defined as an extreme point if each line segment that lies completely in S and contains the point P as an end point of the line segment. So let's take an example. Then let me ask a question. Which of these 3 points, A, B, C, is an extreme point? In this figure, each point A, B, C is on the circumference on the circle as an extreme point of S. So these lines, of course, if you draw a line like this, AB, AC, BC, then each line segments are completely within the shaded area, right? So all of these points A, points B, and point C are the extreme points. How about this? Which of these 6 points are extreme points then? In these figures, points A, B, C, and D, and even E. These 5 points are extreme points of S. What about the F? Although the point F is on the boundary of S in this figure, F cannot be an extreme point of S. That's because this point F lies on the line segment AE. Is that right? And this AE lies completely in S. However, here, the point F is not an endpoint of the line segment of AE. That's why F cannot be the extreme point, okay? And the extreme points are sometimes called the corner points, because if the set S is a polygon, just like this, then the extreme point of S will be the vertices, like this, point A, B, C, D, and E. Or the corners, right? There are 5 corners in this polygon. And the feasible reason for any LP will be a convex set. And the feasible reason for any LP has only a finite number of extreme points. And also the optimal solution is an extreme point of the feasible reason. So I would say that any LP that has an optimal solution has an extreme point that is optimal. Okay. So concept-wise, this is very important. So keep in mind. Okay, so I'm going to stop here for today. And next time, you will learn how to use the graphical method for solving the linear programming problems, especially for the case of only 2 decision variables. Okay, so I will see you next time. Thank you very much. Bye-bye.